So the goal this week is to look at more sophisticated approaches to numerical integration that can deliver much greater accuracy than, or depending on how you look at it, much greater efficiency than the Newton-Cotes rules and composite rules that we saw last week. So you can either get comparable accuracy but with far fewer function evaluations, or for, depending on your perspective, for fixed number of function evaluations by any method, get much greater accuracy with what I'm showing you this week. So today we're looking at a technique called Romberg integration, which is actually based on a more general technique called extrapolation to the limit, or Richardson extrapolation. And then on Thursday we'll look at Gauss quadrature. All right. So the idea behind Richardson extrapolation, also known as extrapolation to the limit, is that whenever you're computing some kind of approximation, which is what we've been seeing lately with composite integration rules or numerical differentiation, the approximation depends on some spacing h. You're evaluating your function f at selected points, and all of the equal spacing h between them, and as the spacing h goes to 0, your approximation converges to the exact answer with some rate of convergence, like order h to the p, h squared, h cubed, something like that. So if we have some knowledge about how the error behaves, what is the order of accuracy in particular of not just the leading error term, but other lower order error terms, then we can use that knowledge of the error formula to get a much more accurate approximation with very little extra computational effort. Okay. So now, so you get an idea what I mean. Here we have as an example the center difference approximation for the first derivative. So f of x naught plus h minus f of x naught minus h all over 2h. And one of the homework problems for this section is to actually show, using Taylor expansion, that the error has this form, that you have some constant times h squared plus some constant times h over 4, and so on. The combination of even powers of h, only even powers. And we actually know what the what the constants are in this case. So f triple prime over 6, fifth derivative, x naught over 120, and so on. Okay, now, as an example of how we can get a very accurate approximation of derivative with little work, I've made up this function here, something that's pretty nasty, something that would be very tedious to get the derivative of using analytical means, such as product rule, quotient rule, chain rule. And we're working at x naught is 0.25. So I'm going to use the center difference formula with two different spacings, so 0.01, and then I cut that in half of 0.005. Now, since in this case, of course, I can compute the exact result, what happens is, if we were to use the center difference for these values of h, here are the errors that we get. So 0.003, and then because the with a larger value of h, and then since this is known to be second order accurate, if you cut h in half, that should reduce the error by a factor of roughly 4. And then this is what happens in this case. So it's almost it's a little more than this error over 4, so 0.00077. So these are pretty good approximations, but can we do much better by combining these two approximations? So that's what Richardson extrapolation is about. So the idea is, I'm going to find d1 of h to be the approximation of its derivative obtained using the step size h. So then, the approximation is equal to the exact result minus this error term that's order h squared. And then we have additional error terms that are order h to the 4. And then I do the same thing with h over 2. So I just replace h by h over 2 throughout here. And we see what the error terms look like. And sure enough, because it's second order accurate, the error is reduced by a factor of roughly 4. So now, if I take this second approximation and multiply both sides of this by 4, now the leading error terms are the same. So now I can just, so now I can cancel these. So that's what I do. I take this approximation, or this equation, minus this one. The leading error terms cancel. And then I divide by 3. So really what I'm doing is I'm using this equation and this equation, taking linear combinations of them, to solve for the exact value, d1 and 0. So the exact result is now equal to this combination of my two approximations. And the error is now order h to the 4. And the thing is, once I've computed these two approximations, there's hardly anything left to do. I just have one multiplication, one subtraction, one division. So no matter how much work is needed to compute these, the actual extrapolation process, which is what you see here, is very quick. Okay, I got a notification of a raised hand. Is there a question in the virtual meeting?
Yes, sir. I was just wondering that in the very last term, when we are writing for d1 at 0, should we have the error of oh h to the power 4 a negative term, because it should subtract from the original term?
Oh, not when it's big O notation.
Okay, okay.
Because
So
all it says is we have this plus some constant factor times h to the 4.
okay, so its sign doesn't really matter. It only matters that. Okay, great.
Yeah, not when it's big O notation.
Okay, thank you, sir.
Yep. Okay, so here's just an illustration of extrapolation, but here's a general formula. So what it relies on is knowledge of the order of accuracy of your approximation, whichever kind of approximation you're using, and the order of the next term. So, we're saying here our approximation is equal to the exact result plus the constant times h to the p, and then if we were to get rid of this error, the error would become order h to the 4. Okay. So then, after computing the approximation of spacing h, I now consider h over q. Now, typically something like h over 2. So q is usually 2 in these cases. So now I just go ahead and compute this approximation. And then this linear combination of my two approximations gives me the exact result plus lower order error, so order h to the r instead of order h to the p. So, so it does require detailed knowledge of the error to have an idea of what you're getting. Because suppose this required two approximations. Suppose I computed a third approximation, like so at h, say h over 2, h over 4. I can extrapolate between these two. That's this. I can extrapolate between this one and a third one. And now I have two higher order approximations, order h to the r. I can even extrapolate between those to make it even more accurate. Here's an example of that. So as I mentioned earlier, here are my two approximations to a derivative. Here are the errors that I got. So I carry out the extrapolation using this formula. So standard difference is second order accurate, so q and p are both equal to 2 in this example. So I go ahead and carry that out, and notice the error is significantly smaller. So here we had 7.7 times 10 to the minus 4. Now I have 3 times 10 to the minus 6. Okay. So here's where I get greedy and want even more accuracy. Well, first of the questions, just about getting down to this point.
So we're assuming that h is very small, I assume, like at least less than 1.
Well, for this example, that shows a 0.01.
Okay.
Yeah, so it didn't have to be terribly small.
It's just, coming from a computer science background, it's kind of weird to think that O of h4 is better than O of h2, h squared.
Oh, yeah, so definitely less than 1. Yeah, because we get the exact result as h goes to 0. That's the key.
Right.
Okay.
Okay.
Oh yeah, I guess you're thinking of like runtime of algorithms,
Yeah.
where whatever you're taking big O of is not a spacing, but a number of operations.
Typically,
Yeah.
Inputs.
Yeah. So for instance, in the second semester of this sequence, when I talk about algorithm complexity, matrix vector multiplication being order n squared operations is definitely better than matrix multiplication that's order n cubed. So, okay. So here we're going to 0, lowest power of h is dominant. Okay. Now, I had approximations with spacing h and h over 2. So now I do a third approximation, h over 4. So the original spacing was 0.01, and then I have, here I have a 0.005, and now I have 0.025. So the error is somewhat smaller. So now, I go ahead and extrapolate between my h over 2 and h over 4 approximations, so my second and third. Same formula, because all these approximations are second order accurate. And now I have this error that's 2 times 10 to the minus 7, which makes sense because these two approximations here and here are fourth order accurate. You reduce h by a factor of 2, the error should reduce by a factor of roughly 2 to the 4th, or 16. And that's kind of what we see here. Now that I have these two fourth order approximations, I extrapolate again. But watch the numbers, they're different now. These two approximations were second order accurate. These are fourth order accurate. So here I have an exponent of 4 here, and here. But keep in mind the formula, whatever order of accuracy you're trying to cancel out, you have to take that into account in the coefficients of this formula. So now when I combine these two in the right way, then the error got smaller still. 2 times 10 to the minus 10. So several orders of magnitude gain. And again, very little effort taken. So you compute 3 approximations to your derivative, and then just a few operations, arithmetic operations on them, wipes out the first 2 error terms and gives you something far more accurate. Now, here's the thing to be careful about, though. This doesn't always work as advertised. And the reason why is we're assuming that the error has this form, but what are these constants? These constants are higher order derivatives. So in this case, we're approximating first derivative. These constants, k1 and k2, are higher order derivatives. What if these derivatives don't exist? So if the function is not very smooth, then the error may be larger than we expect, and this kind of cancellation doesn't work as well. It does work fairly well for derivatives. And the reason why is, as long as these derivatives exist, then we can trust that these are the right constants, and we're canceling out the errors we expect. But what if we use this instead of derivatives, integrals? So if we approximate an integral using a composite rule, like a composite trapezoidal rule, and then perform extrapolation on that, then this can work, but again, it depends on how differentiable the function is. So this leads to a technique called Romberg integration. And the easiest way to describe Romberg integration is you're using the composite trapezoidal rule in conjunction with Richardson extrapolation. So you compute several approximations to the integral using composite trapezoidal rule that's shown here. And here we have the error, where the unknown point c is some point in the interval ab, and times minus 6 squared over 12. Okay, so since we know that this is the error, we'd like to try to cancel that out. And to this point, I've only shown you this error formula. What I've not shown you is that we actually know a lot more about the error than that. It can be shown that the error can be expressed as the sum of terms involving even powers of h, just like for the center difference formula. And that comes from what is called the Euler-Maclaurin expansion. I've not taken the time to cover this. However, if you, actually I'll refer to the textbook a little bit later. It is in the book, the derivation of that expansion, which is what justifies the use of extrapolation, that we know the error consists of even powers of h, terms involving even powers of h. Because if this was all you knew about the error, then fine. You could use Richardson extrapolation to cancel out the leading error term, since you know it's order h squared. And then whatever term is next in the error, that becomes the leading error term. How do you know what that is? H cubed, h to a fourth, h to some upper power? You don't know. But at least with composite trapezoidal rule, that has been investigated, so in that case, we do know. Okay, actually, what I'm going to do, I'm going to stop sharing for a second and then reshare my whole screen. We'll have the book up. Okay. Let's see where I have this. Okay. Yeah, so the star in the case is an optional section of the book, not necessarily to read on first reading. So I didn't assign anything. Okay, I did assign one thing from the section, but it doesn't really require reading the section. Okay. So the Euler-Maclaurin expansion comes from analyzing the error in the composite trapezoidal rule. And I'll scroll to the final result. Okay, here it is. So the exact integral is equal to the composite trapezoidal rule approximations shown here. And then here we have a very elaborate expression for the error. So we have these terms involving even powers of h, only even powers. And notice what was multiplied by. We have certain constants that come from the Bernoulli numbers. But this part is of particular interest. Odd derivatives of f at the endpoints a and b. Now, the reason why this is interesting is because suppose the function f is periodic, and the period is compatible with the interval ab. So like, for example, suppose f is 2 pi periodic and the interval is 0 to 2 pi. Then the derivatives are also periodic. So these values are also equal. The periodic along the continuous means that f of a equals f of b, but these are also equal. So in other words, these error terms just go away. And the thing is, this expansion is r equals 1 to k, but as long as the function remains differentiable, you can carry this out as many times as you like, that the error just keeps getting smaller and smaller. So what that means is, if the function f is periodic and like infinitely differentiable, then this trapezoidal rule approximation, or composite trapezoidal rule approximation, is extraordinarily accurate. Normally it's order h squared, but in the case of a periodic function, what we get is called superconvergence. Convergence faster than any power of h. So you can say that the error is going to 0 exponentially as h goes to 0. So when you have periodic functions, even though we have more sophisticated integration techniques than this, the composite trapezoidal rule really is the best way to go in that situation. So to show you Romberg integration, here's the integral that we'll try. And you choose an initial spacing. We're integrating from 0 to 1, so we'll just use h equal 1. So our first approximation is just, it's not even a composite trapezoidal rule, it's just a basic trapezoidal rule, where I'm going to reformat this fraction. So sorry, this thing is uncooperative again. Okay, so the trapezoidal rule is b minus a over 2 times f at the left endpoint plus f at the right endpoint. So that's all we have here, and here's the error. And then we do it again. Here's a composite trapezoidal rule, and we use twice as many subintervals. So here we only have one interval. Here we have two. So a trapezoid from 0 to 1/2, and then a second trapezoid from 1/2 to 1. Whereas here we're spacing, the coefficient in front was 1/2, now it's going to be 1/4. Okay. Okay. And because the trapezoidal rule is, the composite trapezoidal rule is second order accurate, sure enough the error decreases by a factor of roughly 4. Now that I have two approximations to a trapezoidal rule, I can now perform Richardson extrapolation. This is the same formula as before, it's just rearranged. Whenever you have a second order accurate approximation. So it's equal to the more accurate approximation plus the difference of the two divided by 3. And this approximation is fourth order accurate, and we see that the error is substantially less. Now, watch how I'm indexing these approximations. I'm actually I can store them in a matrix. So the first column, where 1 is the second index, those are composite trapezoidal rule approximations. When we're in column 2, so the second index is equal to 2, that's when we're doing extrapolation, the first extrapolations. So now I do composite trapezoidal rule one more time. The spacing of h of 1/4. So whereas here I had 2 trapezoids, here I have 4. So from 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, 3/4 to 1. So the composite trapezoidal rule gives this error that's roughly 1/4 of this error, as expected. But now that I have these 3 approximations of trapezoidal rule, so T11, T21, T31, I can extrapolate between these two, just like I did these two, and that's what happens here. So I'm using T31 and T21 to give T32. So now I have 2 fourth order approximations. And we see that the error decreases more rapidly between them as the spacing is cut in half. Finally, I carry out extrapolation one more time between these two fourth order approximations to get a 6th order accurate one. And actually the error, it is less, but it's not that great. Yeah, and with integrals, that can happen because it depends, the key variable the error depends on. The error depends on h, spacing h to a power, and then higher order derivatives of the integrand. So how well it works really depends on the integrand and how it behaves on the interval AB as a whole. But this is a process. So here, because we have 2 fourth order approximations, the denominator is now 15. So it's always a power of 4 minus 1. So here we have 4 to the first minus 1, 4 squared minus 1. If we had multiple 6th order accurate approximations, and then we want to go to 8th order, the denominator would become 63. So 4 cubed minus 1. If I show you the algorithm for Romberg integration, here it is, that can be translated fairly readily into MATLAB. Now, the way it works is you're filling in this matrix T, capital T. So when you're filling in the entries in the first column, those are for composite trapezoidal rule approximations. And then in later columns, second column, third column, and so forth, then you, oh, you know what? I think there's a typo here. Well, let me check. Oh, no, that's correct. Never mind. Okay. Here's where extrapolation is carried out. And notice here, we always have increasing powers of 4 minus 1. So that fills in what's called a Romberg table, where you're filling out the matrix. But you're only filling. But notice that K is always less than or equal to J. So really, you're only filling out. So the matrix you're filling out with these approximations is lower triangular, because the row index is always greater than or equal to the column index. Okay.
It is similar to the divided difference table.
In terms of storage, yes.
Yes.
Yeah.
And we don't need to store it in a matrix. We just need to store it in the length of n or j here, right? We can convert this.
Well, because once you extrapolate, then those lower order approximations, you don't need them anymore.
Yes.
So yes, you could overwrite.
Yeah.
Okay. But there is another inefficiency in this algorithm, the way it's written in here, because here I just have a formula for a composite trapezoidal rule. But here's something to think about. If you look at go back to the example. So, because when you're performing numerical integration, a goal is to minimize evaluations of your integrand f. But look where I evaluated f. Here, 0 and 1. Here, 0, 1/2, and 1. 2 of the 3 points were reused. Here I have 0, 1/2, and 1. All of these reused again, and then the new points, 1/4 and 3/4. Also, that should be exploited so that whatever information you use here, you reuse down here, and then adding in whatever new function evaluations. And I've worked that out here. So here we have the composite trapezoidal rule, and the summation in the middle is broken down into odd numbered and even numbered terms. So then, if I take f of a, the even numbered terms, and f of b, and I combine those, that is 1/2 of a trapezoidal rule approximation of twice the spacing. And then I have the odd number terms over here. So when you reduce the spacing from h to h over 2, the new trapezoidal rule approximation is equal to 1/2 the previous one plus these new function values you still need to compute. So that way you can significantly reduce the number of function evaluations needed to compute the first column of your Romberg table. All right. Actually, here's the example that I have that I was doing in the notes with this Gaussian integral. Okay. Right. Anyway, okay. So questions about Romberg integration and how it works. So really all the work is here. Once you have that, very little left to do, just to combine the approximations in the right way. I should mention that when I took the counterpart to this class as an undergrad, this was in fall of 1988, one of the final exam problems was to actually carry out Romberg integration on paper. And you use a calculator, thankfully. But yeah, so I had to fill out, so basically what you see here in this example, this kind of situation where you compute a few trapezoidal rule approximations, then you do 2 rounds of extrapolations to get a first 4th order accurate approximations and 6th order ones. Yeah, I had to do all that. It was not fun. But I remember thinking like, well, maybe we'll get this one at least. It's just incredibly tedious. But yeah, so yeah, when I have given in-class tests, I've not been that sadistic. But because now I can pull the whole thing like everyone's parents or grandparents do. In my day, I had to do this. Okay. Good times. Okay. Now, yes. So here's one of the homework problems from this section, where you write a MATLAB function that implements the Romberg algorithm that I've just shown you, and then try it out on these integrals. Since in all 3 cases you can figure out what the exact answer is supposed to be, and get an idea as to how the error is behaving. And what you find is you will get different behavior. That sometimes Romberg integration works better than in other cases. And the question is why? What can lead it to fail? And that's why I mentioned that you take into account the error formula for composite trapezoidal rule. What does it include? If you know that some part of that error is going to be small, then what's left? That could be causing difficulties. Okay. And the thing to keep in mind is that you have in the error formula, okay. Oh, don't have it written here, but I did have it written here. Your second derivative at an unknown point, and that point can be somewhere in the interval AB. But really, as you saw when this error formula was derived, you had the basic trapezoidal rule error on each subinterval with H, and the error for each subinterval was the second derivative at a point inside that subinterval, and then they were combined using the intermediate value theorem to replace it with think of it as an average. Okay. Now, here I've shown combination of composite trapezoidal rule with Richardson extrapolation. So what you could try is a similar idea, combining Richardson extrapolation with, say, composite Simpson's rule, which is known to be 4th order accurate. So you can try canceling out the 4th or H to a 4th terms. Honestly, off the top of my head, I do not know what the rest of the error expansion looks like. I don't know, the same kind of analysis is performed as for the trapezoidal rule. But you can try to find out if you don't know. And see if you can try continuing the extrapolation from there. So, so as long as you know how the error behaves, you know how to extrapolate. But in the case of Simpson's rule, actually do 1 round of extrapolations to make the order H to the 4th terms go away. If you don't know what power of H comes next, then you don't know how to select the coefficients here. Like you can't be sure what the denominator should be. So that's something to be mindful of. Okay. So know your error and how it behaves if you want to keep extrapolating. Now, we have a good amount of time. Do we have questions about, well, anything? Work for the day or homework problems, etc.? Including from anyone in virtual land. This is another one of the homework problems from this section. So just keep a Taylor expansion not going out to several terms. Or the thing is, and you can use a general formula for Taylor expansion, like involving a sum, like let's say from j equals 0 to infinity. To express the error in general. I've been trying this out for like writing out several terms and seeing, as you combine Taylor expansions, the set of difference approximation, which terms cancel and which don't. You can see the pattern. And then the other problem from this section, set number 5, the algorithm is this one. So even though it's from the section on the Euler-Maclaurin expansion, it doesn't rely on that. It's really just see what happens. Like if you use this function as your integrand, and just go ahead and use the composite trapezoidal rule, and figure out what the error should be. So you choose an integer k, so what happens to the error? And the error should be going to 0, but the idea is that how rapidly it's going to 0. Any questions at all? Okay, fine. Right. So Gauss lecture on Thursday, and I'll stop recording here.
So next we will start chapter 10.